Hello everyone, let's talk about medium problem on Leetcode today. Leetcode 979, distribute coins in binary tree. In this, we are giving a root of a binary tree with n nodes, and each node will have some values in it. Um, and there are n coins as well in total for throughout the whole tree. So in one move, we can choose two adjacent nodes and move one coin from one node to another, and move maybe from parent to child or child to parent. And we have to return the minimum number of moves required to make every node have exactly one coin. So that means like there are n nodes and we have n coins. So each node in the end should have one coin, but we don't have to return the tree, but we have to just return the number of minimum number of moves required to actually make this happen. So they have given this example. So in this case, root node has three coins, and then it can give one coin each to its children. Then everyone will have one coin, and this will require two moves. Similarly, in the second example, the left child has three coins again, and then it will also distribute one to the two to the parent, and then parent will also distribute one to the right child. So in this case, there will be three moves because of that. So now that we have seen the example, let's jump into the solution space. In example one, it was easy to send coins from parent to child because parent has two left and right pointers as shown here, right? But in example 2, it becomes heavy because how can we traverse back from say leaf node to parent node, because we don't have any parent pointer. So one way is like we convert it to the graph and then do different calculations using DFS. But what comes to mind when we look at example 2 is what we can also do is we can do post-order traversal. There are three cases that we can think of. It can be root node, which may have some value, and then we have to distribute those value to the remaining left and right subtrees, right? Or it can be some node in the middle of the tree, which will take or give some values depending on its own value within the tree. And the third case is like if we are the leaf node, we know already that whether we require the what do you say coins or whether we have to give. So we start with the third case, right? Because there's a clarity there. We have already solved the problem for that point. And once we solve it for the child or the leaf nodes, we can actually solve it for its parent and then its parent and for the root. So now let's jump into the algorithm part. Let's take some bigger example. The idea is simple. We will start with the post-order traversal, and we will return, like in each step of the DFS, we will return the number of coins back from the left and right subtrees. So these coins will like if the coins are more than 0, that means we have excessive coins, right? And so that means we can share it with the rest of the tree. But if it's less than 0, that means the um, left child or right child, whichever sends his coin, has a requirement for the coins. So that means we should send it through some other nodes in the tree. And if it's equal to 0, that means there is no movement. So these two cases will cause the movement. So that's how the algorithm will work. So for us, the idea is simple. We will get the coins from the left side. Let's call them coins left. And we'll get the value from the what do you say coins from the right as well. You can call it coins right. And for the current node, so for example for this node, the value will be equal to the coins we have got from the left child plus the coins which we have got from the right child. So in this case it's plus 3, for example, and in this case it's minus 1, plus what you say the coins this child has minus 1. Minus 1 we do because we have to also consume one coin for the current node. So in this case it's 0. So we will add 0, but we'll and then we subtract minus 1. So we will have 3 plus minus 1 plus 0, because the root value does not exist, plus like minus 1 for consuming that node, consuming that coin at the current node. So we will have access of one node, and that's how we will return it to the parent node. So now that you have understood the algorithm, now let's do the dry run. We start with the post order traversal. So suppose we reach the leftmost child where the value is 4. We know now that this leaf child will actually consume one for itself and share rest with the remaining tree. So we get +3 here. Similarly, we because we are doing post-order traversal, now we will process this child. In this case, this child will require one coin because it's 0. So we will return -1 in this case. Now at parent level, we can see parent value is also 0. So that means this parent also requires -1, or like has excess coin. It does not have excess coins. So we will subtract the value by 1. And this will again return in like we get +3 from here, -1 from here. And then -1 again occurs at the parent level. So it will become 3 -1 -1, right? So it will be equal to 1. So we send it to the parent, what you say, root node again. But we have to still process these right childs, right? So we will go to the, say, leftmost child of the right subtree for the root. We see that this one has one access, so we send it back to the its parent. Similarly, for 0, we again send -1, and this will return and say result in 0 access node from the children for this node. But this node already has one value in it, so that means it's coins neutral, right? And that means we will just do +1, right? -1, so no coins, +1 for the current value, -1 again. So this will return in 0 excess coins. So we will send it to the parent. And now we see that parent, in this case the root node, has no value at all. So it will also consume 1 from this child, and that's how we are done. And the important point to consider is like whenever there is a move, either from the left, either from the children to the parent or for the parent to the children, we will add them as to our number of moves, and that will be our answer. So in this case, we moved like we moved 4 coins between this part of the tree. Then we moved 1 coin to the root. And similarly, here we moved 1 coin to the parent, and then here we moved 1 coin from parent to child. So that's how we will calculate the number of moves, and in total we will get like 7 moves based on it. Now that we have understood it, let's jump into the code part. Let's jump into the DFS part. So we will just say helper like root, and what we have to define is like we have to define like we will always return number of extra coins in that particular DFS. If root, like we discussed earlier, if root is equal to null, it does not need to be balanced, and it does not have any excessive coins as well. So we will just return 0. Similarly, we will now calculate coins left, which will be equal to helper root dot left, right? And similarly, coins right will be helper root dot right. And once we have it, we will have how many coins we will have in a total. Initially, it will be like coins left, like these coins left, and like we discussed earlier, coins left and right can be positive or negative depending on whether we have abundance of coin or whether we have shortage of coin on each side. And now we will update it further based on root dot value we had. So like we discussed, like when its root dot value is 1, it's like coin neutral. And then we will also define, say, this, we can, like in Java, it's not easy to pass by reference for integer, so better is passed by value. So I can define moves as one of the private fields. We can also pass like an integer array or something and do the manipulation accordingly, but that makes code less clean. Now we will just do math dot absolute of the coins we have collected so far, and then we will just return the coins, right? Yeah, so remember that DFS is just returning the excessive coin, not the number of moves. Moves are calculated on the way, and now we will just return the moves. So that's it. Now just run this code. Yeah, now let's submit. And cool. So in terms of like time complexity, because we are processing each node only once, so it will be O of n, which is equal to number of nodes. And in terms of space complexity, it will be O of height, but for a very unbalanced tree, it will be O of n again. So I hope this was clear to you. If it helps you, please like and subscribe the video, and please post in the comment how I can do better. Thanks again. Have a nice time.